Hey guys, today we're going to be reviewing synthetic division and the remainder theorem. So synthetic division is basically a shorthand way for doing long division on a polynomial that is divided by a linear binomial. To do this, the first thing we need to do is we need to decide what numbers we're going to be using throughout the synthetic division process. So we know that in the divisor, right, the x minus 2, if we wanted to represent this in our long division, we would have to use the opposite sign of what we see here. So the opposite sign of what we see here would be 2, and that 2 is going to go on the outside of our division. Okay. Now, as for the polynomial itself that is being divided, what we are going to do is we're going to take the coefficient of every term in order from exponents highest to lowest and write them on a line. So x cubed, the coefficient is 1. Minus 4x squared, the coefficient is minus 4. 2x, coefficient is 2. And constant of 4 we bring along. So now, to perform the synthetic division process, the first thing we do is we bring down that very first coefficient, okay, which is 1. So what we're going to do with that coefficient is we're going to now multiply it by that divisor value and place it under the next column. So 2 times 1 is 2. Okay, now that has a stacked set of values that I'm going to add as I see them. So a minus 4 plus a 2 gives me a minus 2. I'm going to go back and multiply. This number on the outside, 2, times minus 2, gives me a minus 4. And then I add going down. 2 minus 4 would give me a minus 2. And then I do it one last time. 2 times minus 2 gives me minus 4. And we have 4 minus 4, which is 0. All right. So we have all the values, but what does this mean as an answer? Well, basically, we are now going to take these values in this lowest row right here and turn them into the coefficients of our resulting polynomial. And the resulting polynomial will start with the exponent exactly 1 less than the leading exponent. So here we have 3. So this 1 is going to be the coefficient of an x squared term, and we know we don't have to write 1. This minus 2 is going to be the coefficient of the x term, and minus 2 is going to be the constant. Now, this number right here at the end, this 0, would typically represent whatever our remainder is. Now, we don't have a remainder, so that's good. So our final answer here for our division is this quadratic right here. So let's try one more synthetic division. Again, how do we set this up? Well, we take the opposite sign of what we see here. So it's going to be a negative 3 on the outside. We create our box. And now, again, we want the coefficients of our variables, exponents, highest to lowest in order. Now, we have x to the third has a coefficient of 2. X squared has a coefficient of 4. But we are missing a term. Okay? We are missing our x term. So what we do now, if we are ever missing a term, is we make sure that we create a place saver, right? We know that this could be rewritten as plus 0x. So in our synthetic division, we are going to create a place saver of 0 for that x term. So that way we have a representative in each column of all the powers of x that are possible in the question. Now that we've set it up, we perform the process of synthetic division. So bring down the first term, multiply it by the outside, which is a negative 6. Stack it in the next column. 4 minus 6 gives me a negative 2. Negative 3 times negative 2 gives me a positive 6. Stacks in the next column. 0 plus 6 just gives me 6. Negative 3 times 6 is a negative 18. And minus 5 minus 18 gives me, I believe, a minus 23. So now all of these values are becoming my coefficients. Now, what is the power of my resulting answer? Well, it's 1 less than this exponent of 3. So 2x to the second power minus 2x plus 6. And then we have this remainder of negative 23. Okay, now how do we handle the remainders? Well, just like we would make a remainder into a fraction with numbers, we're going to turn the remainder into a fraction by putting it over the divisor, which is that little binomial we have here, x plus 3. Now the negative can go be included with the numerator, or we can also write it as minus that remainder. Okay, but both of these would be correct answers. So now there is something that we need to pay attention to in terms of these remainders. There's a little trick. If you wanted to know if a question was going to have a remainder, there's something called the remainder theorem that helps us figure that out. And that remainder theorem states that when a polynomial, let's call it f of x, is divided by a binomial x minus a number, the remainder is the polynomial evaluated at a. Okay, meaning we're plugging in the opposite sign of whatever I see there into our function and getting the answer. So if we are asked to find the remainder when that is divided by one of these binomials, right, this 2x cubed plus 3x squared minus 17x minus 30 divided by one of these, to find that answer, I take the opposite sign. So in this case, for a, we would take x equal to 1 and plug it in. 2 times 1 to the third plus 3 times 1 squared minus 17 times 1 minus 30. Now that's going to be negative 42, which means that when I divide this by x minus 1, I should get a remainder of negative 42. Okay, let's try it again for b. X minus 2. What are we going to plug in? Well, we're going to plug in the opposite sign. So we're going to plug in x is equal to a positive 2. So I plug that in. 2 times positive 2 cubed plus 3 times 2 squared minus 17 times 2 minus 30. That's going to be a minus 36. So what does that mean? Well, when this function, right, this polynomial, is divided by x minus 2, I get a remainder of negative 36. Now, if this was a short answer, you definitely would want to show the substitution. But we're here to try and maximize the points that we're going to get. So one way to get a nice evaluation for these without plugging it in every single time and typing it into your calculator is actually to use the graphing function of your calculator. If I plug into my y1, 2x to the third plus 3x squared minus 17x minus 30, and look at my table, I can actually get all of the values for the given things I'm supposed to be plugging in. So, for example, we wanted to know what happens when I plug in x equal to 1. Well, when I plug in x equal to 1, we already saw that it was negative 42. It works out. X equal to 2 was the next one I wanted to find. Well, x equal to 2 gave me negative 36. Great. So how can I use this table to find the rest of them? Well, here I want to look at where x is equal to a positive 3. That will be 0. Okay, so that's the remainder when I divide it by x minus 3. What about here where x is equal to, and we want a negative 1 this time? Well, I will get a remainder of negative 12. How about minus 2? I will get a remainder of 0. And last but not least, we want x equal to minus 3 here. When I plug in minus 3, I get minus 6. Okay, so those are all the remainders. Now, this would be helpful if you wanted to, make sure you got a question right. This is a quick way to check. If the question directly asks you what the remainder is, of course, this is a valid way of solving it. But this is really a building block to helping us identify factors, okay? Because we use factors for a lot of different things, like finding zeros, etc. So by knowing if something is a factor, right, we open up the possibilities of solving a particular polynomial. So basically, the factor theorem states that if you apply the remainder theorem and you see that the remainder is 0, then that particular binomial is a factor. Okay, so what do I mean by that? Well, based off our previous results, which binomials are factors? Well, they're any one that when I plugged it in, I get 0. Okay, f of a is equal to 0. So let's take a look. Of these, which ones give me a remainder of 0? Well, that's x minus 3 and x plus 2, which means both of those two factors, both of those two binomials are factors. So x minus 3 is a factor, and x plus 2 is a factor. Okay, so that's the idea behind the factors theorem. It's that if you plug in the value and you get a value of 0, you can identify that particular binomial as a factor. Now let's tie it all together. Why is this important? Well, if we know the factors and we know how to do if we know at least one of the factors, I should say, and we know synthetic division, we can use all of this to identify all of the zeros of a particular polynomial. What do I mean by that? Well, if I were to ask you to find the zeros of this, we know that we are looking for the values that, right, make this equal to 0. Now, if you try to do factor by grouping here, it is not going to work. When you group them, they don't give me the exact same parentheses. So one method to finding the zeros of something that is not easily factorable is to go look at your graph or look at your table or use the remainder theorem to find a factor. So since we've already been working with this, let's take x minus 3 is a factor. This was found using the remainder theorem and the factor theorem. So what does that mean? Well, that means x minus 3 divides into this evenly, being multiplied by some other polynomial. Well, how do we find this polynomial? Well, that's where the synthetic division comes in. Okay, what is x minus 3 multiplied by to get that remaining parentheses? So how do I do this? So synthetic division, we take the opposite sign. We do our coefficients, so power of 3, power of 2, power of 1, constant. All right, so we didn't need any place savers. We bring this down. 3 times 2 gives me 6. This is a 9. 3 times 9 is 27. That's a positive 10. 3 times 10 is 30. All right, so we know that it checks out because we have a remainder of 0. And so what goes in that parentheses? Well, one power less than the leading. So that's x to the third. So this should be 2x squared plus 9x plus 10. All right, so now this problem now becomes x minus 3 and then 2x squared plus 9x plus 10 equal to 0. So now we have a quadratic. If we're trying to find the zeros, we have two options. We can A, check to see if it is factorable, or B, use the complete the square to find the answers. I'm going to check that it's factorable. So I'm going to look at 2 times 10, which is 20, and look for two factors that multiply to 20 and add to 9. And the ones that I'm going to use are plus 4 and plus 5. Okay, remember this is the A times C grouping. Now I'm just going to use a different color so you could see my process of factoring. So since I was able to break it up, I'm going to use grouping. So I'm going to take out the GCF of 2x with a leftover of x plus 2. In the second group, I'm going to take out a 5, and I'm left with x plus 2. And then my parentheses are x plus 2, 2x plus 5. And then, of course, the x minus 3 that we should be bringing along. All right, so we've now factored this. Even though it wasn't initially factorable, we were able to use the remainder theorem to make it factorable. And then we can find our zeros. Now, x minus 3 equals 0. Shouldn't be a surprise that we find that x is equal to 3 is a 0 because we know x minus 3 is a factor. Same thing to x plus 2. We know x plus 2 is a factor, so we should expect that x equals minus 2 is a 0. But the one that would have been trickier to find was this one because it's not a perfect value in my table. So that's what this process was to help us find. So our 3 zeros are the following.